Come in and have a seat.
What's up? Right here. Not great. Well, what? Hello, we're on TV.
Put them on TV again.
We're on there.
Okay.
Where'd you find that?
Got the count.
And I was like,
That's right. 17. Okay.
Yeah. Okay, everybody.
Are you going to be here?
Everybody's got their belly full, ready to hear all about nuclear engineering, right? Be introduced to Dr. Lee Dodds, Department Head of Nuclear Engineering. He's going to tell us all about it and I think get a little tour of the whole place. And we're all on TV.
You got it.
All yours.
All right. Let's zoom in. Hey, not only can you play right now, but we're going to archive this. This is being webcast live right now to cyberspace. And we will archive it. And if you'll send me your email address, I will give you the URL, and then you can go home and see it at least for the next 2 weeks before we replace that particular spot on the server with something else, okay? Well, let's get started. My name is Lee Dodds, and I'm the head of the Nuclear Engineering Department. I'm also a native Tennessean, and I assume that everybody here is from the state of Tennessee, is that right? We have anybody from West Tennessee? All right, we're in West Tennessee. Memphis. Anybody from Jackson?
I was born there.
Oh, okay. All right, well, I grew up there. That's my home. My mother still lives there. What we have planned for you today is first of all, I'm going to give a presentation. Should take about 30 minutes or so. Tell you all about nuclear engineering. And then Dr. Art Ruggles, professor of nuclear engineering, and then probably also Dr. Larry Miller are going to take you on tours of our facilities this afternoon, okay? Rather detailed tour, much more detailed than I normally provide when I recruit students. So let's get started. Now you can ask questions at any time, or you can wait at the end. If you do ask a question, my director over here, say I'm the producer of the webcast, and there's the director. He will flip to the second camera. There's a camera right there, and zoom in on your face to hear your question, okay? So keep that in mind. And the other camera is back here in the back of the room, the one that's on me at the moment. Okay, so let's get on with it. This is what I'm going to be talking about. I'm going to give you an overview of our department, and then I'm going to talk about the nuclear engineering job market. Everybody seems to be interested in jobs, and so I put that near the top of my presentation. Then I'm going to give you some specifics about the nuclear engineering major, of what you'll be studying. And in particular, we have a special concentration within nuclear engineering called radiological engineering. And it turns out that that particular concentration satisfies all the requirements for medical school. So, and then I'm going to give you some work examples, and I guess I need to be looking at this over here. Some work examples. What type of career, what type of job would you have if you got a degree in nuclear engineering? And then I'm going to conclude with a description of some unique attributes of our department and some contact information. So if you have questions, just let me know. Our department was founded in 1957. We've produced over 1,000 graduates in the past 46 years, and they've all gotten first-choice engineering jobs, first-choice jobs. Some kids go to medical school. Some recently have gone to law school. We have 9 faculty members. This past fall, that's when we count heads in each of the programs at the university. We had 156 students. That's a small program relative to the other engineering disciplines, right? Mechanical engineering has several hundred. EE has several hundred. This is 156. Yet, We are the second largest nuclear engineering program in the United States. The only one that's bigger is at Texas A&M. And everything in Texas is big, right? Most all of our facilities, not all of them, most of them are in this building, the Pasco Engineering Building, where we have classrooms, faculty offices, laboratories. We have an undergraduate student lounge, which you'll see this afternoon. And we have computing facilities just for nuclear engineering students. You can't get in there. It's a lock on the door unless you're a nuclear engineering student. And needless to say, we have close ties with the Oak Ridge National Laboratory. Get that out of the way. And TVA, Tennessee Valley Authority. All right, Jerry, what's going on? There we go. Okay, let's talk a little bit about the job market. As I said, we've had 100% job placement in the past 46 years. I'm not sure any other departments can say that. Typical employers are General Electric, Westinghouse, Duke Energy, Entergy, TVA, Southern Nuclear, NASA. In fact, one of our professors came to us after working 15 years for NASA. Government laboratories like Oak Ridge, Sun Microsystems, they recently hired one of our PhD graduates. And that Sun, of course, designs computers, sells computers. The Sloan Kettering Cancer Institute and any hospital in the country has to have a nuclear-trained person to either be a radiation safety officer or a medical physicist, okay? And we produce people like that. Starting salaries are BS, $60,000 a year. We just had 4 students go to work for nuclear utilities, and it's remarkable that all 4 got basically the same starting offer. These are starting salaries, $60,000 a year. For the MS degree, it's like in the mid-60s, and then a PhD can be anywhere from the mid-60s to 110. The PhD student that went to work for Sun Microsystems about 6 months ago, his starting salary was $110,000 a year. We are the highest paid engineering discipline offered at UTK, and you can see this on this particular slide here. This is a salary survey that's conducted by the National Society of Professional Engineers each year. This is the 2002 salary survey. 2003 survey is not quite out. And what I have plotted here, or shown on the bar chart, on the horizontal scale here, I've got the median annual income. So this includes starting engineers, and includes engineers about ready to retire, and engineers in between, okay? So young engineers, old engineers, all ages. There are about a total of 7,000 data points total in this survey. And what I have on the vertical scale here are all the engineering disciplines that are offered here at UT, okay? And I don't know which one you might be interested in, but they're all listed here that are offered at UT, and you can see where nuclear is. Now, nationwide, there is an engineering discipline that makes more money than nuclear engineers. It's called petroleum engineering, okay? They have petroleum engineering at a few schools, one like Texas A&M, for example. But petroleum engineering is not offered here at UT, and so it's not listed here. These are just the disciplines that are at UT. All right, now I want to give you some idea of the resurgence that's going on in the United States in the nuclear business. So I got some headlines from the local newspaper that came out last October, and I made 3 slides. There are 3 headlines here, and I want to show it to you. First headline was in the front page or the editorial page of the Knoxville News Sentinel lab, and by the lab they mean the Oak Ridge National Laboratory, which is 30 miles away, returns to its roots. It started during the Manhattan Project back during World War II. It had a nuclear basis for its beginning, and now they're returning to nuclear. This guy here is Gordon Michaels. He is the Director of Nuclear Programs for the Oak Ridge National Laboratory. And now let me show you another headline. Space Program. Security projects spur need for nuclear material. Almost all the space probes, like this is the Cassini space probe, use a radioisotope for power source, and in particular, it's usually plutonium-238. Okay, it's a nuclear material. These space probes wouldn't work. These satellites wouldn't work without this particular radioisotope. So it's really important if you're going to explore space. And then the third headline, again, has to do with space. And I put this one up here because this guy here, he looks like he's, what, about 80 years old? He's actually, because of his gray beard, he's actually a graduate of our department. He graduated in the mid-'70s, early '70s. Cheryl Green is his name. To put men on Mars, you're going to have nuclear power. You cannot get a spaceship from Earth to Mars and back without a nuclear power source. This can't be done, and that's what he's saying right there. Okay. Now, what are you going to study if you study nuclear engineering? What are some of the subjects? Here's a list of most of it. Nuclear reactor analysis, design, and safety. Radiation transport and shielding. So you don't know very much about these topics right now, but if you study nuclear engineering here at UT, these are the things you're going to study. Heat transfer and fluid flow. Instrumentation and controls. Nuclear fuel cycle and waste management. Fissile material safety. Health physics, medical physics. What about the special concentration that we have in radiological engineering? Where does that fit? What is radiological engineering? Well, radiological engineering addresses and deals with the design and safe utilization of radiation and radioisotopes in industry and medicine, okay? And I'm going to give you some examples of that. And the curriculum, what's different about this versus the traditional nuclear curriculum is that we replace 3 engineering courses with 3 biology and chemistry courses, okay? And when we do that, this curriculum satisfies all the requirements for medical school or dental school. Simply, you do have to add on this 2-hour lab that we don't require. And that goes with the second semester of organic chemistry, okay? This is a lot of students, in fact, one of the more popular areas, disciplines, engineering disciplines today is biomedical engineering, okay? This is just as good, if not better, than biomedical engineering. Because you saw where biomedical engineering rated on the salary chart, right, versus nuclear engineering. Keep that in mind. All right. Now I'm going to give you some examples of the type of work you might do if you get a degree in nuclear engineering and you go to work. And by far the biggest place of employment is in the nuclear utility industry. 20% of our nation's electricity is produced by nuclear power. In the Tennessee Valley, TVA, 28% of TVA's electricity is produced by nuclear power. And as you know, nuclear does not have any air pollution associated with it. There are no emissions from a nuclear power plant. So what is this coming out of this? What is this thing, first of all? We've seen it on TV many times. He raised his hand first. What is it?
Nuclear reactor.
Yeah, but what's coming out? First of all, the reactor's right here. Okay? That's the reactor. You're right. The whole thing's called a nuclear plant. But what is this thing that I'm trying to, right there, that I've got the arrow on right there? What is it?
The cooling tower.
That's a cooling tower. It's a heat exchanger. It's nothing more than like a radiator on the front of your car, but this is a water-to-water heat exchanger, really water-to-air, because what's coming out of the top of this cooling tower? Steam, just simple water vapor. A lot of people think it's some kind of contaminated or radioactive smoke. It's just a cloud. It's just water vapor. All right. And I've already mentioned space applications. This is just another pretty picture with some astronauts out here. These facilities are powered primarily by radioisotopes that have to be made in the nuclear industry, usually in a reactor. And then we use radioisotopes in just, you wouldn't believe, over here in Alcoa, Tennessee, where we have a rolling mill. You know about Alcoa, where they make sheet metal for Coke cans and all right. They measure the thickness of the sheet, the aluminum sheet that comes out of the rolling mill with a nuclear technique. Okay, it's a real thin sheet that's coming out. They put a radioactive source on top of the sheet and a detector on the bottom of the sheet, and the radiation coming from the detector is attenuated by the sheet. The thicker the sheet, the more particles get attenuated. and you can calibrate that thing, and you've got a continuous measurement of the thickness of the sheet, which is really important to the aluminum industry. The same concept that I just described is used in the paper industry. The same techniques. It's very important when the pulp comes out. That's where you're going to make paper from the pulp, right? They dry the pulp and you make paper. The thickness of that sheet of pulp is very important, and the same nuclear techniques that are used in the Alcoa plant are used in most paper mills. Nuclear techniques are used to help us find oil, and once you've found a well, you want to know how much oil is in the bottom of it and the quality of the oil. Nuclear techniques are used to do that. Most people don't realize that. And then, of course, radiological examples, processes for the diagnosis and treatment of diseases such as cancer, neutron capture therapy. That's a new technique for treating inoperable brain cancers called glioblastoma multiforme, okay? It's not even approved yet in the United States. It's approved overseas in Japan and in some areas of Europe. It's using neutrons to selectively kill cancers that you can't operate on in the brain. And for me personally, I had a good friend that died about 6 or 8 months ago of glioblastoma multiforme. And we didn't get this technique to him fast enough, okay? Maybe it could have helped him. And then in medical research, radioactive tracer elements are used all the time. We also use nuclear techniques to determine the pollutants that are in air pollution. It's called neutron activation analysis, and it's just like a fingerprint. You can do an activation study of the pollutants in this air and identify what's there. Once you know what's there, you know where it's coming from. And then the government knows where to go and stop it, right, if it's coming from certain places. Now, this particular project discipline is something that I'm really excited about. We've all seen on TV the third world countries where little children are starving to death. There's not enough food. Millions of people starve to death every day, particularly in third world countries. And it's what's really strange. Most of these third world countries, they don't have power, electrical power, to speak of, and therefore they don't have refrigeration. And as it turns out, they produce enough food to feed themselves and to prevent that starvation, but they don't have the refrigeration to prevent the food from spoiling before it gets to the starving people. Okay, it's produced in this side of the country, and you got to truck it or take it on camel to this side of the country to feed the people. Well, it spoils before it gets there, and then they can't eat it, and they starve to death. This is a nuclear technique called food irradiation that will extend the shelf life of almost any food 2 to 3 weeks. If we can bring this technology to third world countries, we can literally save thousands of lives. And so I'm really excited about this, and we've had 2 senior design projects that dealt with this particular subject. All right, now for some unique attributes of our program. We have abundant scholarships, okay? Over half of our undergraduate students have some type of scholarship. And we have, there's one scholarship that I control, and then there's 4 or 5 others that only nuclear students can apply for, okay? And as it turns out, about half our students, slightly over half, have some form of scholarship. But everybody here is from Tennessee, right? If you were from one of these other states, you wouldn't, students from other states have to pay out-of-state fees, right? Not if they study nuclear engineering at UT and they're from one of these states. It's called the academic common market. So if you've got friends in other states, you might want to tell them about this, because it's worth, with a recent increase, that $7,500 is now, it's about $8,000. It's equivalent of an $8,000 a year scholarship. You don't have to pay out-of-state fees if you study nuclear engineering at UT, if you're from one of these states. We also have, we participate in the co-op program, and we help our students get summer internships, which in most all our students are either co-op or they'll do 1, 2, or 3 summer internships. So they've got some experience when they graduate and go to work, and that's really important. We also have a master student program where you can start your graduate studies when you're a senior. Normally, a graduate student takes about 1.5 years to 2 years to get a master's degree, okay, for the average student. But we have a program where you can actually start it when you're a senior, and you can get your master's degree 1 year after you get your BS degree. So in 5 years, you'll get both the BS and the MA, okay? And that's for the better students. And I understand all these students are the better students. Is that right? Very good. So you might be interested in this. And then some other interesting aspects of our program. I said we were small, which means it's easy to go in and talk to the professors, or it's easy to come see the department head. If you're in one of the bigger departments, you've got to make an appointment to see the department head, and then you're probably going to see one of his associates. In our department, you don't need an appointment. You just walk right in my door unless there's somebody sitting in there. And usually there's not somebody sitting there. So it's really easy, if you got a problem, to see me or to see any of the professors, because it is on a scale relative to the other departments in our college. It's a small department. And then finally, contact information. If you have questions after you leave here today and you want to send me a question, here's my email address. This is our web page. I don't know if you've had a chance to look at it. There's a lot of information on our web pages. And you're welcome to come back for a visit anytime. You can sit down and talk face to face. Now, most of the information that I've given you, is going to be in this packet that I'm going to give you now. There's in this packet, this is our standard undergraduate application packet. So this contains everything you need to apply to UT. Even if you're not going to be in nuclear engineering, you can use this information. But then we have a lot of nuclear information in this packet. And then there's a hard copy of the presentation I just gave. Okay? So I'm going to pass this around, and then I'm going to go to I'll ask Will to pass this around. But before I do that, are there any questions? Because now's your chance to ask a question and to be on TV in cyberspace. Now, who is not going to be bashful? Because everybody's sitting there with little grins on their faces right now. See? Who has a question that they want to ask? Don't everybody...
You ask a question on every other...
All right, here we go in the back of the room. The guy, the Tommy Hilfiger guy in the blue shirt. Wait a minute, let's home in on this guy here. We're going to put him on. Watch this. Gary's going to get right on top of him. He'll lean a little bit. There you go. Okay, sir, what's your question?
Do you deal with things like getting rid of nuclear waste?
Oh, yeah. Yeah.
Such as that?
Yeah, let me comment on nuclear waste. People seem to be concerned about that. We've been generating nuclear waste for 60 years, okay? And we've been using what I call low technology to deal with it. Have you ever heard of anybody dying as a result of exposure to nuclear waste? Well, I know the answer. It's never happened. Have you ever heard of anybody being seriously injured as a result of exposure to nuclear waste? That's never happened either. We've had this excellent safety record using relatively low technology stuff, like storing radioactive waste, liquid waste, in large 1 million gallon tanks underground. Okay, when the tank starts to leak, and it's real easy to detect when it starts to leak, you just put a Geiger counter on it, and you know when it's leaking. You pump the stuff out of an old tank into a new tank. Okay, I call that low technology, and it's worked really well from the standpoint of safety and the environment. We've had a few leaks, but nothing really serious. Nobody's been injured or even killed, for that matter. Now we have better technology. Now we have the technology to take the liquid, the water, out of the waste and solidify the waste and vitrify it in a glass log and then store the glass logs. Okay, the French are already doing this. And so the technology is there. The French are doing it. And we'll put these glass logs you can do it two ways. You can leave them on site where the waste was first generated, which is what basically we're doing right now, and that works fine, as it has for the past 60 years. Or the recent political decision, and remember I said political, technically there's not a problem. Politically, it may be a problem. We're going to put it in Yucca Mountain, which is a very dry place out in the west in Nevada. And yes, we have research projects that 156 students that I told you we had. 93 are undergraduate students and 63 are graduate students. And a small fraction of that 63 graduate students have done research in nuclear waste. So that answers your question. Any other questions? Okay. Wait a minute. Let him, hold a minute, right here. Raise your hand again. Keep it raised so he'll know who it is. There you go.
How many undergraduate programs offer nuclear engineering?
Okay. Good question. Good question. In the United States, there are 33 nuclear programs of various forms or fashion in the country. Okay, but that includes both departments and programs that are not really a department. Okay, at 33 universities. In the southeastern United States, there are only 3 universities that offer nuclear engineering, and that's University of Florida, Georgia Tech, and Tennessee. And if you consider North Carolina in the southeast, then NC State offers it. Okay, so if you include North Carolina, there are 4 programs basically in the South. And in the state of Tennessee itself, there's only 1, and that's our program. And I'm going to brag a little bit now, because I'm very proud of our program and our people and our students. We're ranked number 11 out of those 33 in the United States by U.S. News and World Report. We are the highest ranked engineering program in the state of Tennessee from all the universities. And it's bragging, I know it, but gee whiz, so what? When you're number 1, you hold up your finger, right? All right, any other questions? You asked good questions. Okay, one more from the guy in the back.
Do you deal with dismantling of nuclear weapons or anything of that sort?
As a matter of fact, we do. And that's something I used to do. But when I used to do real productive work as a professor, now I'm a department head, I'm an administrator. I'm not sure that what I do is productive. But we have research contracts with the Oak Ridge Y-12 plant, okay? And we don't actually disassemble, but when they disassemble the materials and they store the materials somewhere temporarily, we're concerned that those materials are stored safely. We don't want to have, quote, a criticality accident when we store these nuclear materials. And so in our program, we have what's called nuclear criticality safety here at UT in our department. There are really only 2 or 3 universities of those 33 that have this expertise. There's us, there's the University of New Mexico, and then Georgia Tech has a little bit. One of their professors came up and took our short course several years ago, and then the very next year they started teaching nuclear criticality safety. Okay, so they're kind of an offshoot of our program. And so, yes, we get involved with that aspect of it. When they disassemble these things and they store the fissile materials in the warehouses temporarily, we want to make sure that they do it in a safe way so that there's no possibility of this thing going critical. That's called nuclear criticality safety. Okay, and we have a very good, strong program in that area. Right now, it's directed by Dr. Ron Peavy, who's a graduate of Mississippi State and a graduate of UT in nuclear engineering. Any other questions? Okay.
I was wondering if there was any way to convert like weapons grade nuclear materials to like stuff that you could use in a power plant.
That's going on. You've been reading the paper. Did you read today's paper? That's exactly what's happening. And in fact, there's a company called Nuclear Fuel Services. It's an hour and a half toward Bristol, Kingsport area. It's in Irwin, Tennessee. And they have a big government contract to do precisely. They're taking highly enriched uranium from places like the Y-12 plant where you disassemble the weapons, okay? Highly enriched means there's a lot of 235 in it, okay? Well, we don't need the fuel that goes in a reactor, like at Watts Bar, Sequoia, Browns Ferry, is low enriched. It's got a smaller fraction of 235. So we need to downblend, right? We need to reduce the enrichment from the highly enriched stuff to the low enrichment so that we can use it for fuel in a reactor. And NSS has a big government contract to do that, okay? And so that's actually happening. And we're not only doing it with uranium-238, we're also, in the United States, are taking plutonium-239 that was used in a weapon. These are the pits, so-called pits that are used in nuclear weapons. We're taking that plutonium metal and converting it to an oxide and then combining it with uranium oxide. And we've got two oxides right then in the fuel. And that's called mixed oxide fuel. And that's being done also in the United States. And there are two reactors owned by Duke Energy in North Carolina that are going to be producing electricity using mixed oxide fuel, where the plutonium oxide, the plutonium that's in the plutonium oxide originally came from nuclear weapons. So yes, we're doing that. You ask really good questions. These are really good students. Okay.
One of the concerns with Yucca Mountain and the other storage ideas is how to keep these places off limits for people for however long, that
right.
the life is nuclear material. You guys do any considerations on that? I know I've read a couple things on ways that are nonverbal that they try to keep people away.
Well, the material is not friendly. Okay, it's easy to stay away from highly radioactive nuclear material. These vitrified logs, you don't want to go up and grab a hold of one. You can put it in your pocket and walk away. You can't do that. It's a material that's highly radioactive. It's going to be highly radioactive for a long time, and therefore it's very difficult to abscond with some of that material. Okay, it's just not very practical. It'd be the dumbest thing Saddam Hussein or somebody like him ever did would be to try to steal material out of, or anybody else for that matter, out of Yucca Mountain, or even where it's stored right now, which is on site. It's just not something. It takes nuclear-trained people, like some of you may become, to be able to deal with that material. Okay, and surely he's going to have some nuclear-trained material. Okay, he's going to have some nuclear-trained people that can address material like that. But then again, the security around Yucca Mountain is going to be fantastic. Okay, it's not going to be easy to get at that material. And now, other people are concerned, well, you're going to have to deal with it for hundreds of years. Well, we've already dealt with it successfully using low technology for 60 years. There's no question in my mind that we can do it for several hundred years. I mean, it's easy as pie. So it's not a real issue. People, it's a political issue, but it's not a technical issue. If we can get the political people to understand the technical issues, then maybe that'll solve the political problem. You have another question?
Well, I suppose what I meant was more along the lines of what happens if you have, I'm not going to say, humans are going to not be here in the near future. What happens if you have something happen and a group of people that knows nothing of radioactivity or any of those concepts? What happens if they come upon this site? Intriguing.
Mm-hmm.
You've got to think, if we fail to convey the message that this is a storage place for very highly hazardous waste that will cause injury, death to living things, if we fail to convey that, then what happens when the archaeologists of the future find this place, this gigantic complex buried within a mountain, putting signs all around in a language they don't understand? So
you're assuming that humanity as we know it somehow disappears for at least a period of time, such that there's no history of people. There are no people around there, and then all of a sudden this new group of people show up I'm kind of rephrasing your question here, and they don't understand this, or they don't. All right, let me ask you what you just described. Let me ask, what do you think the probability is that that's going to happen?
Well, I'm not really for sure, but I mean
Can you give me an estimate? What do you think? Just a guess. And you're a real smart guy. I can tell that by your question. Can you give me your best guess estimate as to the probability that that's going to happen? Is it really small or what?
I would consider it small.
Very good. Right, I would too. In fact, extremely small. Extremely. The probability that the scenario that you described, in my opinion, is the probability is epsilon, where epsilon is a, you know about epsilon? Where epsilon is a small number that approaches zero. You're going to learn about epsilon when you come to UT and you take math courses. Have you been proving theorems in high school? You know what I mean by epsilon, right? Okay. That's an excellent question, and people are concerned about that, but I'm not concerned about it. To me, I'm much more concerned about the air pollution right now in the Tennessee Valley and what it's doing to the lungs of the citizens of the state of Tennessee and generally me in particular. And you know where most of that air pollution comes from? It's burning fossil fuels, either burning gasoline in cars or coal from fossil power plants like TVA. And that doesn't mean I'm against fossil fuel. I'm not. I'm just saying I think there's a better way to produce power that's better for the environment and better for people. I mean, sure, nothing is without a little bit of waste, and we produce less waste than anybody, and it's easy to control. And we've demonstrated that it's easy to control for 60 years with low technology. Okay, do we have any more questions? You guys really come up with good questions. These are really good students. How do we get these students? Who selects the governor's school?
They apply.
I do this?
Selected out of a lot of people.
Wow. Congratulations. All right, okay, one more question and we'll start the tours.
What would you suggest as an alternate fuel source for vehicles and fossil fuels?
Oh, thank you for asking that question. Thank you. Hydrogen for vehicles and also for some other applications. We have the technology to power vehicles right now with hydrogen stored in a tank. Okay, that's been demonstrated. It's a little bit costly right now, and one of the reasons it's costly is because it's costly to produce hydrogen. But guess what it takes to produce hydrogen? There are two ways to produce hydrogen. One is with electrolysis. You did that in high school chemistry. Another way is by thermal techniques. Heat. If you have a large heat source, you can. There's thermal fractioning process that will produce hydrogen. I'm not familiar with the details, but both cases, electrolysis and lots of heat means you got to have a concentrated energy source to do that. Either to produce electricity for electrolysis, right, or concentrated energy source to produce the heat for the thermal fractioning process. So guess what that concentrated energy source is? Nuclear power. So hydrogen is the way to fuel vehicles of the future. President Bush said that in his State of the Union message. You know, he wants a 16-year-old that's born right now, 16 years from now, when the person turns 16, that they go take their driver's test driving a hydrogen-powered vehicle. He said that in the State of the Union message, right? And I support that 100% because I know where the hydrogen is going to come from. It has to come. The only safe, environmentally sound way to produce electricity and therefore hydrogen, or to produce large heat sources and do the thermal fracturing process, is with nuclear energy. Yeah.
What would happen
with a nuclear reactor inside your car if you got into a car?
We're not talking about a nuclear reactor inside. I would never propose that.
Nuclear material inside your car.
We don't need that. Yeah, going back to your previous question, hydrogen. It's not a nuclear material. It's H2O. We produce hydrogen using electricity. And so we don't need a nuclear, although if you did it right, you could do that, but that's probably not going to happen. All right, we do one more question, then I've got to let you guys go on the tours. You asked wonderful questions. And if you have more questions, you can send me an email, right? And I'll respond. It's 4 o'clock in the morning. I'll sit down, wake up. I can't go back to sleep. I'll answer my email. So I'll answer your email.
So, do you mean like you burn hydrogen, like in a combustion engine
Yeah,
or something?
yeah.
Okay.
That's been demonstrated.
All right.
I've seen vehicles that burn hydrogen. It's costly right now. One reason it's costly is because the hydrogen is costly. And so how do we get large amounts of economical hydrogen? Nuclear power. So there's a really bright future for nuclear in the United States and the rest of the world. All questions in the future come by email, right? Let me go get Dr. Ruggles, and then just sit right there, and we'll let you pass these around.
You guys want to carry these, or you want me to just keep them until we get back to Esther Room? Okay. You got a promise? Look at all of them. Read them all tonight.
Let me introduce Dr. Art Ruggles. Dr. Ruggles comes to us from the Oak Ridge National Laboratory. He's been a faculty member here for almost 10 years. His area of expertise is thermal hydraulics, which is heat transfer, fluid flow. You saw that on my slide here, okay? He's going to show you some of those facilities that he and his graduate students have, research facilities that they use. And then he's going to go get Dr. Larry Miller, and so you get to talk to another
Tag team tour.
Yeah, this is
being
the
broadcast worldwide.
That's right. That's right. I just introduced you worldwide. That's right.
Oh my, that's scary. Well, let's go. Let's move around a little bit. Let's show you the building.